Awesome. Sounds good. Well, yeah, first of all, thanks guys so much for doing this. Really excited to have you. And yeah, an opportunity to learn this. If you guys want to do maybe quick intros, and I think we can just dive in.
Sure. Sasha, you want to start?
Hi, yeah, I'm Sasha. I have a PhD in distributed systems. Previously, I worked in VMware research and then Novi, and then joined Aptos like 9 months ago, almost 10 months ago. Yeah, working mostly on distributed systems.
Similar for me, I'm Rati. I did PhD in distributed algorithms, MIT, worked at Novi before this, and then joined Aptos.
Yeah. Hi, I'm Jordan, also known as Daniel. So I just graduated this year and had a PhD on consensus, and I joined Aptos recently.
Yeah, thanks for having us, Sergey. It's a pleasure to sort of talk about this. So yeah, I'll just go ahead. So basically, we'll talk about Block-STM, which is a parallel execution engine that we developed. As I said, I'm Rati. I'm presenting, and this is joint work with Sasha, Daniel, George, Zikun, Dalia, you, and Bruntia. So just basically just a very high level sort of overview of things. As you all know, at least currently, the architecture of blockchains is sort of this layered architecture. So we have a consensus layer agreeing on the block of things. We have execution, and we have like some storage or authenticated storage. And all we want to say on this slide is to just motivate, because we've gotten this question before, like, because depending on different blockchains, there are different bottlenecks. But we believe that every component is important, because if you have one component that doesn't scale, the whole system will not scale. Like it's not too deep. It's just the purpose of this slide. But yeah, and our focus for this talk and for this work is on the execution layer of the blockchain. And now to zoom in onto the execution layer. So the way this works is, yeah, we agree on a sequence of blocks. And then when we do agree, let's say like we have to execute the block that has been agreed on, B2. Every validator will go and execute the transactions in this block. And it's really important that actually the transaction output of executing will be deterministic. And then this deterministic output will be sort of applied to the storage. And then basically we'll continue the next block from here. So what are the approaches for doing this execution, right? There is obviously we can just go and execute transactions one by one. This is like, there is nothing deep here, and I mean, the problem with this is that we want to make it faster, because sequential execution tends to be really slow. So again, like when we have a system and it's sequential and it's slow, of course, the attempt, like the first idea is to try to use parallelism. And there are ways and there are chains out there that already that utilize, even before we started, I guess, working on this project, because we also do now use Block-STM in production. But there are other approaches, but they tend to sort of rely on user-declared dependencies. So basically, there is this block. It contains a bunch of transactions, and then somehow there is usually some sort of hints about where these transactions are going to write. Mainly, it's usually the writes, not the reads, but yeah, and we will dive into this a bit more later. But on a high level, the problem of this is that this tends to be a bit limited. So if you're limiting, so if your hints turn out to be wrong, the transaction may need to be broken up. It may need to be retried, and it's also and if the user is asked to declare these dependencies and the hints for the write sets, it's also somewhat not ergonomic, because now you have to do extra work, and you may have to guess where it's going to write if it's like some secondary index. So these are some of the drawbacks of the approaches before us, I would say. So what is our design goals, right? Motivated by this. So we wanted to build a parallel execution engine that would be transparent to the users. So from the user perspective, you would do exactly the same thing, regardless of whether we were running this load sequentially or in parallel. But we would want to sort of exploit the parallelism. And we also want our system to be adaptive to the workload. And what we mean by this is because obviously the workload itself dictates how much inherent parallelism can be sort of there to even make use of. Like, for instance, if every transaction depends on, like, has a conflict with every other transaction, there is really nothing you can do because there is this critical chain of dependencies. So that's the second bullet point here. In this case, we know we cannot be faster than sequential execution, but we want to introduce as low overhead as possible because we want this to be a real system. On the other hand, let's say if there are few conflicts, we want to extract as much as parallelism as possible. So we want to, like, standard concurrency sort of design goals, like we want to scale somewhat linearly to sort of adding number of cores, etc. So now if we dive into some of the prior academic work, there is this cool sort of paradigm called minor replay, which was introduced in 5 years ago. And the idea, and then there has been like follow-up works, but the main idea basically utilizes this asymmetry in a lot of blockchain systems. So it's called minor replay because maybe it's like sort of motivated by the mining and proof of work systems. But it does apply to sort of proof of stake systems as well, because you can view the miner essentially as a leader that's proposing the block. So in this case, the main observation in this line of work is that the miner or the leader is the first one that has access sort of to this to the block, and it can be the first one to actually execute these transactions. And maybe this will be slow, but then it can sort of there are approaches how it could extract the dependency information between the transactions as it's executing it. And then it can send this information to other validators to help them execute faster. And there are many ways, like locking schedule, and actually a lot of this subsequent work has been basically compressing this information, making it more efficient, coupling it with some sort of static analysis, etc., etc. But usually the idea is you now the validators, the other validators, non-leader ones, would have transactions, but they would also have some hints as opposed, like that's coming from the leader, that would tell them sort of what transaction has a dependency on what else. And then the problem becomes significantly easier. Essentially, you can just do like a fork join schedule and run things that have dependencies resolved with maximum amount of parallelism that you can afford and is available, like and is needed. What is the problem? This is a pretty good approach, but what are some of the drawbacks of it? First of all, so validators, other than the leader, benefit from this, right? They actually become a lot faster because you don't have any conflicts, you don't have anything to worry about. You can essentially be as optimal as you need to be. But the leader still has no hints, so it still has the problem of having to execute these transactions in some way to make it fast. So we're not really helping the latency here for like end-to-end. The other thing is we are introducing some level of trust to this sort of dependency information. So if it's Byzantine, it could actually, you need some sort of protection to make sure that your performance doesn't get really bad if the information is actually wrong. And as I said, like in order to make it this more applicable and practical, there is sort of the subsequent work did assume that you would be doing some sort of static analysis or pre-computation, which is an like additional assumption. There is one work that Inspire does a lot, and that is very, very related, which is from the databases community, and it's a system called BOM. Basically, what happens there is this system executes transactions according to a fixed preset order. And what I mean by this is essentially like if you have transaction, like the outcome is always the same as if you executed this transaction in a given sequential order. Because our requirement, as I said, is just like for blockchain perspective, it's just deterministic. So it's theoretic, like essentially it's from blockchain perspective, it's fine if you have sort of some order, not necessarily known ahead of time, as long as every validator gets the same order. And what BOM is doing is stronger. It says, well, our serialization is exactly going to be the same as this order that's determined before. Like serialization is determined ahead of time. The interesting thing is that BOM requires the right locations to be. BOM requires an overestimation, or like an estimation of right locations. And this can be done by static analysis or pre-execution, or can be user provided. One thing is that because this work was done in databases context, transactions there are sort of, I think they're simpler, there are store procedures, et cetera, So this is actually a weaker assumption from the databases community than would be in general, or for blockchains, I would say. So the way it works is it uses sort of this data structure where, as I said, so we get an estimation of where each transaction is going to write, and we're going to allocate basically a slot for every estimated write per location that is written, right? So let's say in here, there are like 6 writes that are estimated to a particular location. Now we can know exactly where to read from, right? Because we know that these transactions have to be basically the outcome should be the same as executing them in a given sequential order. So let's say if transaction 8 comes, it knows, or maybe this is a value 7 on this slide. I'm sorry, but basically like you can always read from the highest estimated entry that is lower than your index in the serialization, the predetermined serialization order. If you show up and you see that this location is not yet written, you wait. And here is sort of another detail that comes into play in BOM, which is basically because we might have overestimates. Whenever a transaction finishes execution, it has to basically, like, it will write to some subset of the locations that it was like estimated to write. And it should also mark the other locations as basically that, like, I didn't end up writing here. So the other threads that are trying to read from there can sort of do a traversal below and find what they have to read. But these are basically all the details, what this paper deals with. But the main assumptions I outlined in the bullet points. It's a great paper. But so from our perspective, what are the drawbacks? As we said, it requires right estimates. And we want to have like arbitrary smart contracts, et cetera, So this is a big assumption. Like, we want to avoid sort of having to provide right estimates. In particular, sometimes it's very hard to have proper right estimates if you have things that like secondary indices where you read something and then you read the next thing based on the value of what you just read, because this is very hard for static analysis and many other techniques. And another drawback of BOM is that so it's okay to overestimate. Of course, if you overestimate too much, it introduces some inefficiency, but it's not bad. I would say it's like almost linear, or it's really sort of not that bad to overestimate. But unestimated writes are terrible. Anytime you make a mistake and the transaction ends up writing to a location that it wasn't estimated to write, there is nothing the algorithm can do, and the authors outline themselves that in this case you pretty much have to restart the whole execution from scratch, taking this new location into consideration as an estimate. And finally, one work that's very relevant and we also took some inspiration from was software transactional memory systems. These are like Dijkstra award-winning papers from 93 and 95. And this is essentially a framework to atomically execute arbitrary transactions. It was designed basically as a framework for concurrency. So people could write code and then sort of the underlying framework would run them concurrently, right? With optimistic concurrency control, it's basically a way of building the systems. And with such a design, each thread, like on a high level, what happens, it picks a transaction, it executes it. Afterwards, at some point, it validates that whatever it read when it was executing the transaction is sort of still valid. Like, so if this validation fails, it has to re-execute the transaction, and otherwise, there are techniques that basically guarantee that this transaction can be safely committed. Unfortunately, software transactional memory systems are rarely used in practice because they often don't provide very good performance, or in other words, like for any specific problem, there is usually ways to design a specific solution and use like synchronization primitives such that it will outperform the software transactional memory based approach. And also another issue is that generally the outcome is not deterministic. So software transactional memory as such does not require the outcome to be deterministic, but it's a very sort of, it has been a very active topic of academic research, I believe. So people have done work to sort of consider STM systems that have a deterministic order. We even found works that consider like BOM preset order as well. However, what we can say about those approaches is usually they treat this as an additional constraint. So they are basically trying to lose as little performance as possible to satisfy this additional constraint. And for us, even the performance of software transactional memory systems, even without this constraint, is not good enough. However, it has been shown that the STM systems can be practical for special purposes, like in certain problem spaces. You can also specialize your STM system in such a way that it can actually be efficient. One thing I didn't mention is please feel free to interrupt me anytime if you have any questions.
I have a
yes
question, I guess, just very quickly. So when you say actually, location or memory, right? Like, what should we think about? Should we think about like in the context of a blockchain, like an account? Is it a transaction? Is it like actual like bytes and like, you're looking at like specific byte location memories?
This is a great question. So I think you can abstract it a way where you say like, let's view, if you view every transaction as like it reads some data, it writes some data, it does some computation, right? The location is basically the granularity of these writes. So I believe at Aptos, we have something called like it's the access path or state key. And this is basically the granularity of which the items are stored and the granularity at which the items are written. These actually don't necessarily need to be the same. Like it could be that in storage, you actually store multiple things together. So not to make it more confusing, it's the granularity in which you could have like read-write conflicts. Like if one transaction wrote something and the other transaction was trying to read the same thing, like this is what I would call a location. Does that make sense? Or?
Yep, that makes sense.
Yeah, it could be accounts, right? But it could be if there are multiple things on an account, and if two transactions could touch those different things concurrently and not have a data race, then that would be that is what we would treat as a location, right? And usually it's basically you can view it as a key value store, right? Like some like access path or like location identifier, and then the bytes that it contains.
I mean, I guess like just in the context of blockchain, right? Like I can see very, yeah, like different extremes, right? Where, for instance, like everybody accesses like the same, AMM, then everybody accesses like, the price exactly, the same location over and over again, like in a block. And then you have other extremes, right? Where people are making payments where everything is actually completely like disjoint for the most part, right? Like everybody's transacting with one another. And yeah, I guess, do you know in practice, are you trying to optimize for one extreme or the other, or is it kind of, or all these techniques kind of work for all cases?
So this technique will basically try, like we do take precautions to implement our contracts in such a way that they have like as little conflicts as possible, because the conflicts will determine the inherent parallelism that we can extract. So in particular, if the load is such that every transaction touches the same, like sort of everybody writes and reads some same even one location, it doesn't matter what anything else, like it can be completely parallelizable. This will basically impose like a sequential ordering on us. We have some research and something that we productionized to sort of alleviate some sort of specific instances of things that parallel execution may touch that would otherwise be a sequential conflict, but usually, yes, usually from the perspective of Block-STM, it will basically take whatever you give it and try to do its best, right? And then there is the other side of designing the contracts in such a way that they have as little conflict with each other as possible. I think if sort of on the blockchain, given that there will be multiple different contracts and so on, we would hope that most of the time, like there would be significant sort of parallelism to extract. Like if someone is minting like million NFTs and a lot of these transactions are like in the same blocks and so on, then it really depends between those transactions. It really depends like how they built their contract, right? Like if they, I think that's the best way to describe it. I wonder, do you guys have anything to add? Or?
No, that's good.
Okay, cool. Does that make sense?
Yep.
Cool, thanks. All right, so
maybe while we're interrupting with questions here, I can just ask for some quick clarification, if that's okay.
Of course, yes.
Yeah, sure. So you said earlier static analysis. Now, when I hear those words, I usually think of like some computationally intensive procedure that's run, at compile time, whatever that might mean. But you use it, the way you use it kind of suggests that you're doing some kind of analysis on the live transaction stream, so you can kind of place them into different buckets that can be run in parallel or something, which is just a little bit, not what I think of when I hear static analysis. So maybe like, am I missing something, or perhaps you can clarify?
Sorry, that just means I wasn't very clear. Thanks a lot for clarification. So what we mean, we actually we do something specific to the algorithm. So all this so far was sort of existing approaches. And when I mention static analysis, I mean exactly what you said, right? Basically, some compilation time checks that tries to understand basically like the right set of a transaction, etc., etc. And when the dynamic counterpart of it is basically like, usually it's like pre-execution, which is like a classic thing that a lot of systems do. Like you take all the transactions and you execute them embarrassingly in parallel from the initial state. Then you, of course, this computation will not be correct, right? Because any conflict will like trigger it to be incorrect, because you're basing everything on the initial state. However, you run them embarrassingly in parallel, so hopefully it's fast enough, and then you use the read-write sets as the estimates, right? So this is basically the most common dynamic way people do these things. Then there is static analysis, and some systems ask people to provide sort of the right sets themselves, right? The users. So I think these are on a high level like 3 different approaches if you need the hints. And what we do in Block-STM is basically some like we basically realized this at some point, like in the middle of designing the algorithm. Like one part of the algorithm can be viewed as an improvement of this pre-execution paradigm. However, it's not like if you just view the system from the outside, we don't say that we need any user provided hints or any hints from like static analysis or anything of that nature. Like we can just, if we have those, actually we can use them to be better, but it's usually like it's actually usually not worth paying that price. I can talk about this a bit more later.
Okay, cool, thanks.
Cool. So what we'll try to do in the next few slides is hopefully give you some idea of like why the blockchain use case has some characteristics that actually make it possible for us to design a specialized and very efficient STM system. First, and some of these are convenience, and some of these are like actually sort of algorithmically important. So like for instance, the first one is that we have this block granularity, right? Like you basically execute a block, you execute another block, you execute another block. Typically the state updates, agreement on the root hashes, etc., like all of this work happens and at the granularity of a block. So, and also we don't need to, this is in contrast with general purpose STM systems, where the system is supposed to handle like an ever like possibly longly like infinite stream of transactions and just keep processing them, right? And in the blockchain use case, we can garbage collect in between blocks. We don't need to have this like incremental garbage collection mechanism, just basically like which we can, it's super simple garbage collection. And also we don't need to track when individual transactions are committed, because like we like at some point it will be like at some point we like during the system execution there will be a specific moment which actually we determine in our proofs that like there is such a moment for like increasing prefix of transactions when they can be considered committed, because they're like they'll never have to re-execute, they're completely we have the correct output. However, we don't need to track this for at the transaction granularity. We just need to know when the whole block is safe to commit, right? And this actually helps when like removing a lot of synchronization and complexity from the algorithm. The second one is VM safety. So in our case, on the way the blockchains are designed is that we have some smart contract language, and we have a VM that's basically executing the smart contract written in this language, right? And it's the VM's responsibility to to basically be able to execute an arbitrary code that can be expressed in this language. And if this code like has a bug and has an error and does something strange, to sort of gracefully just basically, let's say, provide an error message, right? So for instance, let's say, because if you execute things concurrently, you can read completely like things that could not exist in sequential execution. And here is an example. Let's say I can design a contract, and like you can convince yourself, obviously, that if these are the smart contracts, X will always be bigger than Y if these transactions are executed atomically, right? Like first transaction sets X to 2, Y to 1, second X to 3, Y to 2. But if we start executing them concurrently, like step by step, the green thread might write X equals to 2. The purple thread, the blue thread might go and read X. The purple thread might go and like write X3, Y equals to 2. Now the green thread might read Y, also 2, and then divide by 0. And notice that this would have never happened in a sequential execution, right? And normally in a general, sorry, there was, did someone want to ask a question? No?
Sorry, my bad. I had the microphone on.
Yeah, no worries.
Sorry about that.
Yeah, no worries. So if this was running basically in the wild, right, this would crash the system, because we would divide by 0. And the general purpose STM systems have to go like, have to do like some really non-trivial and not cheap things to provide properties like opacity that guarantee that this cannot happen. Like you cannot read like arbitrary things that can cause you to have an execution that you couldn't have before, then crash the system, right? For us, we don't care, because there could be another contract that just tries to divide by 0, and the VM should just return an error in this case, right? So even in this speculative execution that is wrong, if it divides by 0, like the VM will just say that, well, the contract divided by 0, it returned an error. And then at some point, we will realize that it read the wrong thing, we'll re-execute it, and we'll get the correct output. But we don't have to worry about sort of this arbitrary crashes and divisions by 0 and this kind of stuff. So basically, VM protects against, VM has to protect against like smart contract like behavior, and it ends up helping us in this significant way. So the last one that I will emphasize is the preset order. And this is something that we observed, and then like, and we would love to claim that we made this observation first, but it's not true. BOM paper explicitly makes this observation. But I believe, and I think my co-authors also believe, that this is not, people should know this observation way more than they know, right? Like basically the observation is that intuitively it seems that the preset order, like the fact that I'm forcing the execution to be the same, like the serialization, I'm forcing serialization. So I'm basically forcing the execution to have the same outcome as like transaction 1, transaction 2, transaction 3 executing sequentially. I'm not allowing, despite me running things in parallel, or concurrently, I'm not allowing sort of arbitrary more serialization. So I'm actually constraining myself. So, but basically this can help performance, not hurt performance. And the reason for this is actually the following. This is like our way of sort of explaining this, is imagine you have like 2 threads, you have 2 transactions. If the purple, and you're like running, you have this system that executes them and has to determine a serialization. In this case, if purple went first, nobody even knows about the green threads like transaction Y, right? So X would have to get serialized before Y, like in a general purpose system that does not enforce a preset order. And if green goes first, then Y would be serialized before X. And if they are concurrent, it can be one of the two, right? It's basically some interpolation between these 2 extreme executions. And this is essentially, if you're familiar with like Fisher, Lynch, Patterson, the consensus impossibility arguments for deterministic systems, well, obviously this is not deterministic, but it's a consensus-like task, which costs synchronization to solve. Like every transaction that's running concurrently is also solving this problem, trying to decide which one will be serialized earlier. And when you enforce a preset order, I mean, it enforces, like maybe there is a better order and this becomes a different problem to find the best order. But once you fix the order, you remove all the synchronization overhead of agreeing on basically like which transaction gets serialized where. And this makes things a lot faster and a lot simpler. And I think basically BOM very explicitly makes this observation. And we think that we just take it one like a notch higher. Like we basically built a lot more on top of this observation and get a lot more performance, I think, at least for blockchain and our system. So on a high level, the system looks like this. There is an executor which marshals the threads. The threads, there is a basically a component called collaborative scheduler, which we'll sort of talk more about. But this is basically where all the magic of sort of deciding what to do and when lives. And basically threads go to the collaborative scheduler to understand what is their next task. So let's say you call get task, you get an execution task. you go and execute a transaction. For this, we use a VM. We basically use it as a black box. However, we make an assumption which is without a loss of generality, but it's consistent with how our MoveVM works, that the VM does the reads to also a multi-version data structure that we'll explain, that is basically a wrapper on top of storage, but it never writes. The VM executes transactions, but it never actually writes anywhere. It just produces the write set and the read set. It just returns them, it just returns it back to the executor. And then the executor can apply the writes to the multi-version data structure. And this multi-version data structure is a part of Block-STM. It's similar to what I described to you in for BOM, but it's basically a dynamic version of it where you don't have to know ahead of time all the entries. And we also, but because our executions are speculative, they might have wrong output. So the system as a whole, like in general purpose, has to have a concept of validation. So then everything gets validated. And when a thread gets a validation task, it just goes and makes sure that it just repeats all the reads that happened during an execution that we are validating. And it makes sure that it reads exactly the same stuff that was read during that execution. And execution is deterministic. So this way it knows that the results of this execution are still valid. And of course, after performing a task, you have to tell the scheduler that he performed the task. And eventually, when the whole system is done, we commit the sort of results to the storage. Now, multi-version data structure, to explain this like a bit.
Sorry, just a quick question.
Yes.
Before I go, so here everything is sequential, like you get a task, you go through this pipeline, then you get a next task, or you parallelize some of this?
So executor has multiple threads, but each thread basically does this sort of, from a thread perspective, it's like get a task, perform the task, go like update the scheduler, go get the next task. But there are multiple of these threads that live in the executor, and this is where the parallelism comes from.
Okay, thanks.
Sorry, so does that mean you have like different threads can apply like writes parallelly in that case?
Yes.
Right?
Yeah, exactly.
So,
yes.
Yeah. So I guess the question I have is just like usually you have this like notion of like a storage route that depends on like the execution order that you can use maybe for light plans and whatnot. I'm just curious, like if you parallelize, say, the writes, for example, like do you have this notion of storage route? Will it be different as a result? Like how do you manage that?
Right. So I think if I understand the question correctly, there is basically two parts to the answer. As I said before, the storage, at the end of the day, like we will do a lot of speculative executions. The system will do some executions that will just be discarded, like, right? But at the end of the day, like what gets applied to the storage will be exactly the same as executing transaction 1 and applying its output, then executing transaction 2 from this state and applying its output, and et cetera, et cetera. So the route after the block will be the same as if you executed transactions in the fixed order sequentially, right? And even the route in between transactions, if you were to compute that, would be the same. However,
I see.
So this might be counterintuitive, right? Exactly, because how can this possibly happen when it's like a Wild West and everybody is applying all these speculative rights at the same time? And the answer to that is the multi-version data structure, because transaction 3 and transaction 4 apply their rights at a different, because all the way until we write anything to storage, multi-version data structure is part of the system. This is not the final output, right? So here we can be wild. And well, transaction 4 does not overwrite transaction 3. You keep multiple versions, right? Like 4 writes its own stuff. If it gets re-executed, it overwrites its own stuff, right? But this way, 5 reads, it can see what 4 wrote, right? And etc. And if 4 reads, it can see what 3 wrote. And these things do not conflict with each other, which is exactly what I'm basically trying to explain on this slide. Like basically the way that the multi-version data structure will look, it will be like an entry per transaction that wrote, it's per location there will be a data structure that has an entry per transaction that wrote to it. So let's say transaction 1 wrote to some location, transaction 3 wrote to the same location, and transaction 7 wrote to the same location. It will have 3 entries. If transaction 6 comes and writes here, basically it will be inserted at the right place such that we still have a map-like semantics where I can find the maximum thing that's below me, which is useful, which is useful when I do a read. So whenever we do a read and transaction 5 is performing a read, it finds what's the highest transaction that has made a speculative write here. In this case, it's 3. So basically the rationale here is that we are adhering to the sequential order, right? So I know that 5 should, in a sequential execution, 5 should read the highest thing that any transaction before it writes, or if nobody writes, then it should read from storage. So it's the same logic, right? So in this case, 5 reads, value 3. And yeah, does this make sense? It's basically the same thing as in BOM, except it's dynamic. Like we allow you to insert your write into the data structure, as opposed to saying that the data structure is determined statically ahead of time. Now the collaborative scheduler has this global queue abstraction. So it provides this, it provides a way to find the next task. And because we want to, because we are enforcing this preset order of transactions, we have to prioritize execution and validation tasks for lower transactions. And what I mean by that, like imagine we are like in the beginning, like every transaction needs to be executed at least once speculatively, right? But it doesn't make sense for me to go and execute transaction 500 because its behavior is determined by a large part with all the previous transactions. So I should always try to take an available task associated with the lowest possible transaction index. And also validation must happen in order. So, or like logically happen in sequence. So for instance, let's say we execute transactions 1, 2, and 3, and we execute them in parallel, like then we decide to also validate them. And suppose that transaction 2 validation fails. And how can this happen, right? So let's say because we were executing them in parallel, maybe transaction 2 did not see a write by transaction 1. But now when I validated, I saw that actually transaction 1 wrote to some location that I was reading. I should have read that and my behavior could have completely changed. Because of this, I have to the system has to re-execute transaction 2. But this has a side effect that then transaction 3 needs to get revalidated. Because even though it passed, even if it passed this validation before, now transaction 2 can get re-executed and overwrite something that you previously validated. So now you again have to revalidate transaction 3. However, validations are like much cheaper because it's basically just a sequence of breeds. So our general approach is that we optimistically dispatch both execution and validation tasks. And exactly like because of what I just explained, a successful validation does not mean it's safe to commit. And this is unlike the general purpose systems. But a failed validation means that we have to re-execute for sure. And one trick that I think this is something that I mentioned before, that basically we have this, now I basically in the next few slides, I'll explain some of the algorithmic things that I think are novel that actually contribute to the system being really performant. And then the first one is we have this concept of dependencies. So if transaction X tries to read a location that transaction Y is estimated to write, we suspend X and make X wait for Y until Y finishes next execution, and then X goes. Now you might be asking, like, how do we know an estimates? Like your whole design goal was to avoid having hints for writes and so on. Why do you have how can you know that Y is estimated to write to a location? And in order to do this, we do the following following algorithm. Whenever a transaction fails validation and it aborts, so we know what it wrote before. We know this execution was based on some read that was not correct. So we have to execute it. But these writes are already in the data structure. We go and we mark these writes as an estimate. So basically, conceptually, what we are saying is, I executed this transaction from some state, and it wrote to these locations. I have to re-execute it. Let me make a guess that most likely it will write to the, let me be conservative and assume that it will still write to the same locations. So if someone is about to read from this location, let's wait for this transaction to finish, because otherwise we might have cascading aborts. So a read by transaction 5 in this case would wait, because it would say, look, transaction 3 previously wrote to this location, now it's running again. The cost of me bypassing this and later having to abort is much higher than me just waiting, so let me just wait, right? And once we actually built this as part of our algorithm, and then we realized that this is an improvement of a classic pre-execution paradigm. And this is really classic. This is what people have been doing for 30 years in a lot of papers. And the pre-execution is, as I described, you run everything embarrassingly parallel in the beginning, and you use the read and write sets as estimates, right? So what we do notice is that basically, in a good case, if you don't abort, we never have to. So notice that in the pre-execution paradigm, you execute every transaction at least twice, right? For us, it's once, because we only, if it's a good case and things are not aborting, you will just be executed once, right? And moreover, the estimate in the pre-execution is always based on the initial state. And in our case, it's based on whatever speculative state you read when you aborted. And if you keep aborting, your estimates will get fresher and fresher, because they will be based, if you already executed 200 transactions and you're executing transaction 201, it's basically reading all these recent things that transactions 195 are writing. So it's more likely that the estimates that we are getting are much more accurate. And if we consider versus the right estimates that the BOM uses, the big difference here is that if we have an unestimated write, it's not a problem. We just put it in the data structure. And every write in the first execution is unestimated. But once you abort, now you get estimates for the next execution, right? And in BOM, a missed write estimate is a disaster. You just cannot do anything about it. Finally, another sort of innovation on the concurrent algorithmic side is this thing that we designed to pick the next task. Because as I said, it's very, very important to try to pick execution and validation tasks with from available tasks with the lowest possible transaction index. And ordered sets and priority queues, I mean, they scale, and my advisors and his students have done a lot of work on this stuff, and other people, and this is an active area of research in multi-core community, but they don't scale as well. And the problem is usually, if you want to implement a concurrent priority queue, the contention is always everybody who tries to pop is contending for the same element. And this is an inherent problem that is usually very hard to solve. And even if you allow relaxed semantics, that maybe I take it from the first log n elements instead of always the highest or lowest priority one, it still usually, it doesn't give the performance that we would have needed, right? So we basically use something here that is reminiscent of counting sort a little bit, because we use the fact that transaction indices are actually indices. Like we can order, let's say if a block contains 1,000 transactions, we have indices from 0 to 999, right? So what we do is we just associate status with each index, and we basically do traversals. So we just have this active index, and we see whether at this index there is a task. So let's say here there is, for transaction 2, there is no task. So the thread does fetch an increment, goes here, and realizes that for transaction 3, it needs to be validated right now. Then we'll take a validation task, swap out the status, basically. Okay, I took the validation task, so nobody else needs, like, I'll do this. And yeah, and actually, basically, this is it. We just have to, like, if you insert something, it's expressed by basically insert the task. You also have to reset the index to make sure someone will find it. But basically, you can implement a counting-based concurrent ordered set. And finally, some notes about sort of implementation and design. The transaction status is basically the state diagram, like the transaction is either ready to execute, executing, executed. When there is a dependency, there is a special status, etc., etc. And we have to deal with some concurrency issues. One thing that we noticed is that originally we had like very complicated log-free counters for everything, but this fetch and increment that finds the slot for the set actually ends up load balancing things. So we can just put a lock, a mutex on top of the status, and it works just fine and simplifies the execution a lot. And what we can, there is also a choice one can make when encountering a dependency. You can literally like suspend the execution and continue later, or you can crash and basically start re-executing from scratch. But these are like small trade-off details that may even differ from system to system. What's the best solution? Finally, some more optimizations are like, instead of using a single counting-based ordered set for both execution and validation tasks, we have 2 of them. And the rationale is because of this resetting this index. We don't want, like, validation of the tasks can happen multiple times. And if we didn't separate them, we would just be doing some extra validations. The algorithm would still be correct, but it's just an optimization. The other thing is we always try to, because validations are significantly cheaper than execution, we always try to validate like eagerly, like as soon as possible, because it's better to pay for extra validation and catch sometimes aborts early than have something called cascading aborts. So like some transaction reads something that actually is not correct and computes its output, and then someone else reads that, because then you have to like abort this whole chain. And this is usually one of the behaviors that makes like general purpose and other STM systems not performant if there is a potential for cascading aborts. And we have this another like really interesting optimization that we can like when we can basically prove that in certain cases we can avoid to like revalidating certain sort of transactions, even though it's cheap. And we try to avoid reducing this index as much as possible. So sometimes we will violate this principle of taking the smallest thing and just, let's say, if inserting a task, execution or validation task into the set would have decreased the index, the thread that would have inserted it will just do this task. So not to create this fake work for other workers. And finally, this lazy commit is basically related to the thing we said about the block. So we have a way to tell when the block is safe to commit, and we just check this lazily, like we don't track individual commits. And we prove, like, if you see our manuscript on archive, like we have a very comprehensive proofs for safety and liveness. Yeah, just basically we show that there will be no deadlock, no live lock, and the final state will be equivalent to executing the transactions in a sequential order. Finally, the Block-STM implementation is running on the, like, it's already been a while that it's basically integrated both on the original DM code base and on the Aptos code base. our first experiments were on the DM code base because this work was started while we were actually all others were working at Novi. But we have experiments both. We have experiments for both DM code base and Aptos base, and we have comparisons. We compare to BOM and we compare to a recent deterministic STM algorithm, LITM. And for the load, we take peer-to-peer transactions, and we experiment with block size 1,000 and 10,000. And peer-to-peer transactions are good because the number, basically you randomly choose from which account to transfer. And the number of accounts basically corresponds to contention level. Like if you have 2 accounts, basically it's a sequential load. If you have 100 accounts, you're going to have, you have just more dependencies between transactions than, let's say, if you have 10K. In 10K, most of the time, there should not be any conflicts. And like 1K is going to be in between. And some, like, because of some sort of compliance checks, DM has actually, it's not such a lightweight transaction, the peer-to-peer transaction, because people sometimes think that it's just like one instruction, and this is why we get this really good throughput. I mean, it's not a super heavyweight contract, but it's non-trivial. It has like 21 reads and 4 writes. Oh yeah. So I guess, yeah, maybe I'm running out of time. So let me see. The thing that we wanted to highlight here is that we are actually very competitive with BOM. We give BOM, we cannot run BOM unless it has right estimates, and we give BOM correct right estimates for free. So it's actually supposed to beat us, and it beats us for block size 1K, but actually for block size 10, the other way around, actually, yes. It eventually beats us, sorry, but for block size 1K, it was really confusing because we were like, our system was doing better. And then we realized that this is due to the initial overhead for BOM to create this static data structures. Maybe it can have a better implementation, but at the end of the day, the real point is that we are really competitive with BOM. And so I'll skip this, like one more thing here to emphasize. So this is Aptos peer-to-peer transaction, is that, as you see, like just our own scaling, right? With more accounts, obviously we scale better because there is less conflicts, but even with 100 accounts, we scale pretty well, up to 32 threads. And more importantly, one of our design goals was that if you have basically a sequential load, we don't want a lot of overhead. And as you see, like the black line is sequential execution, and the red line is the Block-STM execution with 2 accounts that has a lot of, like it has to do validations, it has to basically abort almost everything. And yet it has maybe 10 to 20% overhead with respect, like compared to the sequential execution. Yeah, I think there is some sort of interesting extensions technically, nested transactions combining with minor replay, generalizing to non-uniform memory access, like multiple socket machines. We also didn't optimize for hyper-threading. This is number one, to not impose like big constraints on the validator nodes to be like some humongous machines. But also it's like, these are usually orthogonal optimizations that one can apply to the algorithm. Finally, this is just for the execution, and a lot of blockchain, as we said, consists of many, many systems. And we believe that, that there is some recent work co-authored by Sasha that made like a big breakthrough in scaling the consensus layer. But even if consensus and execution were result for good, storage could be a major bottleneck. And I think we all believe that sharding is something that's going to be a super important research direction for this whole field. I think that's it for me, but yeah, please let me know if you have any further questions.
Thanks. I have one question. So Do you have any preventive measures for like someone to, like come up with a sequence of transactions that would cause a lot of cascading aborts, for example, like cause, it's like a DOS vector?
So cascading aborts should not be basically the mechanism that should protect against that is the picking the lowest index, because you have your concurrency level in the system, right? And this determines how many transactions are you able to sort of process concurrently. Like, so you're executing them, you're validating them, but until basically, even though we don't track it in our system, like in the proofs and in general, like there is a transaction keeps getting re-executed, revalidated until basically it gets committed, even though we don't track time when it gets committed, right? And as long as a task of the execution and validation exists, our algorithm makes sure that I will take this task before I make a new task, before I take a task for some future transaction. So this limits basically how deep a cascading effect can go. And the experiments where we have a lot of conflicts actually should already be triggering the cascading effect to the, as much as basically it's supposed to show up, right? So what I'm trying to say is basically it's some function of the load and the level of concurrency. But it cannot. But because of the preset order, we are choosing the lowest task, and also because we have the estimates, the effects of cascading aborts in general are like mitigated to a large extent, right? Because in order to have cascading, also like if you see that someone is actively like someone previously wrote somewhere, you will not even finish, so then you cannot be aborted, right? You're like just waiting for someone else to finish that, right? But I think it's a great question. I think it's just at the algorithm design level where you try to mitigate this.
Thanks.
I have just a higher level question, kind of a little bit orthogonal to this. As you try these things, how do you evaluate whether or not something is a good, technique or idea? Do you just run experiments and then give it a try? Do you write down like, the optimistic or ideal execution and like try to do a theoretical comparison against it, just for my own understanding?
That's also a great question. So we were really blessed that we had sort of a real system. Of course, like without it would be very hard. Like we actually have we also have some sort of fake benchmarks and things like that, and they were quite useful. But there is really no comparison to sort of running things on like somewhat realistic, like real transactions and a real system. But of course, yes, before getting there, there is. I think both, like Sasha has done a lot of work previously on like the STM systems, and some of us basically we had like different sort of backgrounds, so some things sort of just made sense, right? Like we knew basically what pitfalls to avoid, and like for instance, like for sure we knew that we are gonna use optimistic concurrency control, because you just know that if you go the other way, probably performance will not be good enough. But this is just basically by like just knowing the literature or having the intuition, right? Or something similar about if we used like a spray list or log-free skip list, it would be efficient, but we like it would like we know those papers and we know sort of the throughput that they get, and it's nice, but probably would not be, we would basically end up a bottleneck for us. Actually, I've not verified this, I might be wrong, but this was again like just this intuitions, right? So actually maybe Sasha do you want to add a few words?
Yeah, I think mostly it's like you said, like intuition, and you try and you evaluate and you see what works, what doesn't work, and like what you said, we had the system and we could actually check, and few ideas we try and eventually we didn't do. So Yeah.
Yes, I think theoretical stuff was super important to us, but it was mainly like just making sure like we really proved everything, and we don't regret it to the day, like because it took a lot of effort. But on the other hand, this lets us sleep better at night because this is actually running in production. And but yeah, I think like just theoretically it would be much harder. There were actually a few ideas that we had that didn't end up working. And then you sort of try to analyze it and understand what is it that you're missing, right? But yeah, it was a lot of trial and error. Daniel, you agree?
Yeah.
Okay, Daniel agrees.
Nice, awesome. Let's see, any other questions? Awesome. Well, sounds good. Well, thanks guys so much for walking us through this. This is quite interesting.
Thanks a lot, and feel free to reach out to us with any questions if you decide to like dive deeper. We hope that the paper is in a decent shape, but yeah, any questions just send our way. And we have a blog post also on the Aptos Medium, and it should be another sort of high level introduction to the techniques used and so on. Maybe if some things were too fast today, hopefully it's explained better there. But we also tried to make the paper accessible. But as I said, like any questions you have, send us our way, and we'll try to respond as quickly as we can.
Sounds great. Appreciate it so much.
Cool.
Awesome.
Guys,
Thanks.
was great meeting you, and yeah, bye bye.
Thanks. See you.